Сейчас у нас будет очень классный доклад про шумных соседей и про то, как...
Friends, want to welcome everyone back. It's so good that you're with us, and now we'll be speaking about noisy neighbors. I want to invite Aleksey Knyazhev.
Я попрошу
And before we begin,
на бота.
could you please put the QR code on the screen? We're asking questions via the bot, and we are going to provide answers after the presentation. It'll be a final QR code for voting, which is very good, and I think we need it, and the speakers need it, and the feedback is great. Over to you, Aleksey. Thank you.
Всем привет. Думаю,
Hi, everyone.
встречались ситуации, когда
I think many of you have been in a situation when like it's 5 a.m. in the morning and some kind of neighbor begins to use the drill and you would wake up and curse them out loud. In Avito, we are facing a similar challenge, but it's not about the neighbors, but about the disk in and out.
и вообще к чему.
And this is how we solved it and what was the outcome of it. I'm Aleksey Knyazhev.
Команде
I'm
в Avito.
an engineer in the DBaaS team. I came to Avito in October 2023, and this is when I've changed my role from the product developer into platform engineer. And now I'm developing DBaaS and limits of disk entry and exit in Kubernetes. I work in Kubernetes database and things like. So what my presentation is all about.
Тому, что из себя
First of all, we are going to cover what the DBaaS platform is all about and what DBaaS in Avito, what it looks like. And then we're going to cover some good Kubernetes abstracts,
посмотрим на
and also we'll look at some prerequisites of building the disk entry and exit limitation, why we decided to use proprietary tool, and we'll see what came out of it.
платформа DBaaS. Давайте постараемся
So, DBaaS platform,
что же вообще такое DBaaS и
what it's all about, DBaaS, and what DBaaS platform in Avito company looks like right now. So DBaaS is basically database as a service.
то есть
So,
собой полную автоматизацию
DBaaS is the full automation of the database lifecycle.
удаления баз
So deployment, deleting database, and sending data for archiving. And as a result, DBaaS is taking off the parasite cognitive load from the product developers. That is basically the product developer in Avito company. They do not work with such experts as database operation directly. So building database without platform is simply like a one command in terminal and you're done. And within minutes, a database, whatever is needed, will be ready.
Итак, к чему мы в итоге пришли? Ну, мы на 99%
So these are some results. 99% we have decreased the time of building new database. Before, this platform database would be done like manually or in semi-automatic with some scripts by some admins of databases, and it would take from 3 to 7 days. Now, because we fully automated this process,
новой баз данных сократилось
the time of building new database shrank, and now it's basically from 2 to 5 minutes. And now you can see stats of those database being built. Oh, something is with my mic.
Так, раз. Меня слышно?
Check, check.
С этого тоже не слышно.
Hope you can hear me now.
Ну, пока постараюсь говорить погромче.
Well, anyway, I'll try to be louder.
Раз. Раз.
Так вот, к чему
So, anyway,
пришли? На слайде можно увидеть
Anyway,
статистику.
this is the outcome. You can see the stats of the DBaaS platform by the amount of storage created. And in 2023 and 2024, in the year 23, it's not a full stats because we have the data only for the Q1, so we extrapolated the data.
На нашей платформе десятки
But basically, on our platform, tens of thousands of storage have been created. These big numbers can be explained because in these stats, it is not only persistent database, database, but also databases created in a test environment. For integration tests, you can create your own database for testing period.
Итак, мы в DBaaS
Начинают
используем в
разговаривать.
качестве рантайм-платформы Kubernetes.
So, as a runtime platform, we use Kubernetes quite successfully. So, we also decided to use Kubernetes because it has a lot of built-in automation. And in this way, we can save lots of time.
Он берет на себя
В микрофон.
On top of that, it also do resource planning and
на основании запросов на ресурсы планировать приложение по
we can plan apps by the cluster nodes. So the result of that is that it's quite easy to service hardware. If you want to take any node and serve it, we basically take it out of operation. Kubernetes is like distributing storage codes to different nodes with available resources, and we take this turn off node for service. For Kubernetes, there are a lot of open source solutions. Some of them we use, others we kind of fine-tune, and yet another ones we use as a source of inspiration, which is also great. And also Kubernetes gives us enables us to be independent from the environment. We provide databases not only in an environment like a pro staging, but also in local environment. A developer can want to launch a test environment, some database, which service depends from, and test the service. So you would like to launch databases, and Kubernetes enables us to unify it. Whenever a developer wants to deploy a data for a local service, they launch a playground from Kubernetes, like a mini Kupoli or something like that. Then within it, there are some operators like we have on the production. And also, the database is being launched like in the same way as it's been done during the production.
Чуть больше про
Now, a bit more about how DBaaS works in Avito. You can use this QR code. There is a playlist from our latest meetup, external meetup. Actually was a great meetup. Please go ahead and check it, because we've seen what the DBaaS in Avito platform is like, why you need it, how we arrived to building it. We checked on how we work with the stateful applications in the Kubernetes, and also we looked for the multi-cluster environment, patterns, because this is our environment. It is not only class from the Kubernetes, but also checked how to adapt classic databases. In our case, it was a Postgres, like how we Postgres, pulled it into our platform, and what problems we have faced.
Итак, Kubernetes.
So, Kubernetes. Let's see what Kubernetes is about, how to persistently store data, and check some main abstractions, which will be very handy. So Kubernetes is like everywhere, like the slide says, quite a popular thing. So hopefully you guys know it, at least on the level of basic aspects. Let's remember what Kubernetes is. In principle, it's an open source which enables to automate deployment, scaling up, and other things related to app operation. It groups containers in pods, some logic units, which are used in planning, deployment, detection, and other applications, use cases. As I've mentioned before, I assume that you know some basic concepts of Kubernetes like pod, deployment, and others. Here we're going to look into persistent things like persistent volume claim. We'll check dynamic provisioning, CSI, and daemon set, because we'll also need it. So, what is persistent volume? It's a resource describing a volume of persistent storage. This could be a disk area on a node, network disk, or something else. Some kind of like persistent storage volume. Manifest looks like this. It's a very simple manifest, which is called test volume. I mean, persistent volume, which is called test volume. 1 gigabyte, and this persistent volume announces like a volume of disk on a node. It's the simplest version. I have to know that in manifest description there could be different parameters because they depend on particular implementation of persistent storage. Could be abstract for network disks, and the manifest is going to look differently. So, if we will apply this manifest in Kubernetes, then it looks like on the node we identify like 1 GB worth of disk area, and this will be our persistent volume. And if we will make a list of persistent volumes, we can see it right here. We can see its name right here, and capacity, access, modes, and the status. It's available. Okay, you have a question. So what do you do with that? And because, okay, we know how to create pod, we know how to create persistent volume, and how do we assemble it into something so that application could be using some persistent storage? It doesn't make sense. Kubernetes has persistent volume chain, or claim, sorry. It requires the user's inquiry for storage. This is the manifest, and that is, we are creating manifest for persistent volume claim. It's a test PVC, its name, and we specify requirements for it. We say that in manifest from the slide we need 1 GB worth of storage and some other spec parameters to go along with it. Let's see what is going to happen if we'll apply this manifest in Kubernetes. Well, as we can see, we have a test PVC, and Kubernetes will be able to find the available persistent volume. Like on the past slide, there was like a two-stage, the status was like available. And also it's going to attach them to one another. We'll be able to see it if you put up the list of persistent volume claims. We can see that it's a test PVC. It's mounted to volume, test, volume. This is the connection. And the status is bound. Let's go back to pod and see how we can use it in our app. In the pod, we can announce the section with volumes which we may use in our containers. And in the volume announcement, we can say that the source of the volume is persistent volume claim. We are using some persistent storage, which will be corresponding with this volume to store the data. And also in containers, we can use these volumes. Like this volume static right here, we mount within the container with Jinx by the wire HTML. So let's see what will happen if we'll apply it. It's logical that the pod is being created, and with this connection test PVC, it will be able to use our persistent volume like test volume. And so we have on the node, you can store data. There'll be like 1 GB where it will be able to store its data. So this arrangement is called static provisioning. So cluster admin has to manually create different volumes, and so the users of Kubernetes will be making like applications, persistent volume claims, and so these volumes will be used. What may be the problem of this method? It's automation. I mean, the lack of thereof, because persistent volume we create manually. Or you can use some scripts, but it's like a semi kind of manual process. So you gotta watch things like, oops, oh, we ran out of persistent volumes, we cannot launch the app, and something else. Or oops, persistent volume claim has been created for 2 gigs and we have only for 1, or for another amount of storage. Like many questions, many issues which as you're using this path may persist, and you may eventually have some problems. So what Kubernetes guys did to be able to avoid it? They have dynamic provisioning. This dynamic provisioning helps you to create persistent volumes automatically, even dynamically. It's neither cluster admin nor users have to create persistent volumes. They do not know all details of these implementations. They're creating on the volume request, that is persistent volume claim, and Kubernetes, due to automation, creates the right fitting persistent volumes. At the same time, Kubernetes in the code base, there was a functionality to identify persistent volumes for different providers. In the code base, there was a code to create volumes for the disk area on the host, for the network disk, and something else. So the code base really sprawled. It was not good. So they came up with a CSI, Container Storage Interface. It's a specification with which Kubernetes can create persistent volumes. An implementation of this specification lies on the stage on the side of the equipment manufacturers, some enthusiasts, or whoever else. Kubernetes do not know about internal logic, like what is going on when you create some volume, a persistent volume. It's all behind CSI implementation. Kubernetes is part of this interface, and this is how you can create persistent volumes, but at the same time without attaching them to some implementation. Now let's check what all this scheme is going to look like when you use dynamic provision and CSI. In this case, we build only PVC, and next container storage interface is tracing the creation of PVC, and next, using its internal automatics, because Kubernetes does not know how it happens. It identifies volume and builds persistent volume. And next, it's pretty much standard arrangements of parts using this persistent volume claim. They begin to use our storage volume and creating, like images or whatever, CATS images. As a part of particular implementation of CSI, in Avito we use Topo LVM. Topo LVM creates persistent volume with LVM, which is a logical volume manager. It creates those volumes on nodes, on the working nodes. And logical volume manager is thing on a Linux which is creating logical volumes without any attachment to implementation, like abstract. So you may have several physical disks connected to a node, but at the same time, LVM sees them as some unified space and cuts the volumes in this single space. One logical tome identified with the LVM physically can be stored on different disks, but we can, set us apart from the implementation, not to think about what disks are connected and whatever else. And Topple LVM supports dynamic provisioning and also volume expansion without downtime. Volume expansion is actually an important thing because oftentimes we get inquiries like, give us more database, the size of it, and we would not want to violate accessibility guarantee and arrive to downtimes simply because we have to increase the storage volume. So in Topo LVM, in persistent volume claim, we change the size, let's say from 5 to 10 gig, and then Topo LVM, with its own automation and its own LVM, increases size of the volume without any downtime. So it happens like seamlessly. Basically, it's a very cool thing, and we've been using it like happily. Topo LVM isolates volumes on the block units level, so you can see them in operational systems. I mean, those volumes are cut by Topo LVM, not as partitions of a device, but as different devices. And what is also important, Topo LVM has integration with a Kubernetes planner, so it calculates free disk space on the working nodes. If on some node we have enough CPU and memory, but not enough size of the disk to launch our database, Topo LVM will not let us to plan for this node, lest you have different like appending codes or whatever, because without this you would have like a code is planned for node because enough CPU and memory, but disk storage is not enough, and persistent volume claim cannot be created. So the part is planned, but it's kind of suspended, and there is nothing you can do about it. So Topo LVM kind of stops this from happening, which is great. And final abstraction, daemon set. This is abstraction which defines app and copies of which needs to be launched on each node of the cluster, like one piece for each. This is the look of the manifest. We also specify it's a daemon set. We say the name of it and some parameters of it. And what is also cool that it's a code template. That if we'll apply this daemon set manifest in the cluster, we'll get the following picture. For each node of the cluster, we will launch one part of our app each, and this part will be made out of templates specified in daemon set. There'll be like one container with jigs if you look from the slide. What else? And if you will put the list of the codes, you can see this beautiful picture.
Итак, давайте теперь поговорим
Now let's see about some prerequisites of it. Why do we need to come up with some things to limit disk entry and exit in Kubernetes?
Мы столкнулись с проблемой шумных соседей.
We got a problem of noisy neighbors, and it's that basically once you launch codes on one node, they split up its resources, and if you do not limit them, then you may have this problem of like a noisy neighbors, so to speak. So if any of the parts is over consuming one split resource, like a disk or a base, if you're speaking about our example, and it begins to write something like really intensively on a disk, it may do the hypernotation of different codes because the bandwidth is being occupied by this kind of overconsumption of a disk entry and exit, and other parts, they simply degrade.
Давайте подумаем, что же может
Now, let's think what Kubernetes can do to solve this problem. Out of the box, Kubernetes has CPU and memory. Unfortunately, there is no support for disk entry and exit, and the same for the network. In our case, this lack of limitations is really stopping production and operation of PostgreSQL in Kubernetes, and this what prompted us to make our own solution. Basically, I have to say that in Kubernetes you do have some initial things for limitation. Like in the new version, they've added volume attribute in class AP. That is, it's an API with which we can identify certain class of storage, and for these classes we can identify some parameters. I mean, as an example, this could be also IOPS and the number of operation per second, and bandwidth, which is bandwidth, of course. Bandwidth. And now, what's the problem of this API? It's an alpha version, is not very stable yet. And secondly, this mechanism have to be supported by CSI provider. So these very specific class parameters, they have to be implemented by a specific CSI provider. In our case, it's a top LVM, and it does not have it yet. Next, the mechanism is not super good for building individual limits of the disk entry and exit, because for each application, because we announce certain global class of storage, and secondly, it cannot, like we say like one volume, but we want to set different limitations for access to this volume from different containers. It cannot do it either. We can set limitation only for one volume, and they'll be identical for all pods and containers which use this volume. Another bad thing, it cannot do the changes in limitations. For example, if you want to change amount of operations per second that you can do in the volume, we have to build new class, and this new class assign for persistent volume claim. We cannot simply change existing class or resource and get changed limits in a runtime. That's why we decided to do our own solution, and let's see how we implemented it.
В общем-то, мы, вооружившись Kubernetes,
Well, basically, using Kubernetes like a do-it-yourself things, we did our own. It's a daemon set operator, which is called IOBA. Its launch is a daemon set, and it applies limitations. I mean, each operator uses limitations at their node.
IOBA расшифровывается как
This IOBA stands for Input Output Bandwidth Adjuster.
вот. Давайте немножко рассмотрим, что
And let's now see what operator is in Kubernetes. Operators are program extensions. In QAs, they do not change as code like as separate applications, and they implement the same principles as control loop and work as controllers for custom resources. So we build some custom resources, which would be similar to what we have like a code, deployment, persistent volume claim. So we build our own resource with our parameters, and the controller gets update of these resources, and then in this resource in the spec field you keep the desired state of the object, and controller based on this desired state brings this kind of like what you want to what's real. And so the operator basically is a set of some controllers for a certain set of custom resources. And this is a code sample. If you use the operator SDK, it generates this kind of function. It's going to be a reconcile function, which basically is going to implement control loop. It will be called on any change of the object, and this function has, of course, announcement section, and then we get our desired state of an object which has already been updated. And also we do some like a super duper cool logic to make sure that this would be actual state, desired state into actual state. And now let's see, how do we apply limits? Yes, on QR code, there'll be a link to a manual. If you like it, you can read it. This manual. And in fact, to apply limits, we use a C group version 2 mechanism. And unlike the first version, why we use this second version? Because IO controller in the C group version 2 can limit, or I would say has more mature limitations of input and output, and it can limit bufferized entry in and out, intro out, input output, which the version 1 cannot do. So the C group is basically the kernel mechanism, and you can create some groups, and for the groups you can set some limitations for the CPU, memory, disk input and output, and also in this group you can add processes. So the processes added to control group, they will be limited in view of limitations that you set for this group. So C group provides an interface in the view of in the form of a virtual file system, where each control group is represented as a file. There could be inserted control groups like inserted files, and within these files there's an interface files where we can communicate with parameters of certain control group. Here on the slide you can see one of the options of the path to such an interface folder of the container launch in Kubernetes. So you have like a general control group for all the codes in Kubernetes. We have control group which is created for each code in Kubernetes, and within this control group we have a control group, another one for each container launched within this code. If we move on into this folder, and we'll see what kind of files we have in it, we'll see interface files of different controllers of C group. And if we'll just do the grep of it, you can see the interface files of the IO controller, the ones we need to limit disk input and output. 4 files right here, related to controller, and we are looking at IO max, and this is how we set limitations of disk input and output for this control group right here.
Ну и если мы выведем содержимое этого файлика, то
And if we'll take out the content of this file, it's going to look like that. There's a line-by-line limitations for each line. It's a number of devices that we need to set limitations for, and limitations themselves. It's a bandwidth, reading, and what else? And for recording, a number of operations per second. Instead of some specific number, there could be like a max meaning no limitations. And also on this slide, bandwidth for recording IOPS for reading are not limited.
Итак,
So, how do we use that in our operator? Well, mostly we create this kind of custom resource like I/O limit. You set limitations on the level of storage with this resource. And we can see a selector of our storage, and this would be the name of the storage, and also name of the set of replicas. And then we get limitations of the disk input and output for this storage. And as you can see, with this resource, you can set individual limits for each container and for each volume. That is, for the same volume, which has been used in different containers, we can announce different limitations. Also, for different volumes used in one container, we can also set different limitations. Now let's see what IOBA will do once it gets resource IO limit. So it follows IO limit resource, gets some kind of update, and then it gets the list of the parts of storage on its node, and then with some kind of mega magic creates a pod IO limit. Pod IO limit. So pod IO limit created for each limitation and for each group. What is pod IO limit? This is more like a low-level resource. It sets limitations on the level of a pod. And the controller, on the basis of this IO limit, for the whole storage gets all the pods, and for each pod creates its own resource pod limit. It creates more like a low-level information, which we can use for applying limitations of C group.
So let's just take a look at this information. There are three interesting fields that there are no in the IO limit resource. These are the ID of the containers, the numbers of the mounted device, the number of the actual volume that we would like to introduce the limitation to, and the UID of the pod. The ID container and the ID pods are required to get the path to the interface group of the container. So they are here, they are set here, and the numbers of the mounted device are required to give the limitations. That's the IO max shown here. So the ID containers should be able to acquire through the iPod containers. Here's the status and the field where we get the state of each of the containers. And the container ID, I can just show you another one. I hope you have seen it. It's stored in the pod metadata, so I decided just not to draw any lines here whatsoever. So as the numbers are concerned with the pre-mount device, it's much more complicated. We can check them with the prox file system. If we just go to the mountain info file, we will see the pre-mounted devices, like here. But a couple of questions may arise. There are some numbers of the devices, but we need to have this string in particular. 254. So the question is, we need to find this file, we just need to take a look at the path, and we need to identify the string, because there are plenty of strings there. So what do these things look like? It's the PID of the container. PID is the tail PID of... We just need to find the tail PID for the host. This UID that we use to find the string basically is a volume handler. It's an UID contained in the system persistent volume. Volume handle is in the specification of persistent volume in some of the parameters that are specific for the container storage interface. As we are getting and obtaining PID, it's getting more interesting. Kubernetes abstracts the user from the logic of the launch of the applications. So we're going to take a logic of the main container PID. learning this with the abstractions of Kubernetes is impossible. So what can we do about it? We can actually break all of the abstractions and find out the PID of the main processor of the runtime interface container. What's this thing like? It's the specification just like the container storage interface. It's the specification with which Kubernetes will be able to launch the containers. So different manufacturers of the software can come up with their own implementations of CRR, and without actually getting much into detail about how the containers are launched, may actually launch the containers. And CRI is gPC IP with some handles to pull, and they are pulled by Kubernetes. We did it approximately like that. What we do is just do the container request to the time interface. There is an interesting container status RPC, which returns the information about the status of the container. That information has a very interesting field of the PID of the main process of the containers in the tail system. What do you think it's going to look like? The IOBA gets resources and limits and gets storage pods, gets the necessary information about persistent volume. Then from the API runtime interface container, IOBA gets the PID of the main container. Then having all of the information, it goes to ProCFS for the number of the devices, and then without any magic, it creates the PIO limit.
Ну и так как ресурс под EU-limit содержит уже все нужные данные, то есть которые нужны.
It contains all of the necessary data to apply to the C group version 2. The controller actually applies these limits, so it applies this to the IO max files. There's nothing too complicated. There may be a question about how we're going to plan it with the top LVM. Top LVM can do it with the planner, so that we are not planning pods and nodes with too little volume space. It's the same here. We don't want to plan pods for the nodes where we don't have enough bandwidth or the I/O operations per second. Let's just take a look at what the planner in Kubernetes works. A planner is a standalone scheduler which will receive each and every created pod, and it distributes all of the created pods by nodes, depending on the requests for resources available. We would like to create a pod. It goes to the kube scheduler, and then we have to have 1500 CPU and 800 megabytes of memory. Kube scheduler checks for the resources available on the node and decides that this pod will run on node 2 because there's just enough resources available on node 2. And it manifests like this. With the container description, we point out the block with the request for resources available, for how much memory we need, how much CPU power we require, etc. Kubernetes allows us to create our own types of resources that will also be taken into account by the planner, like CPU resources and the memory resources. For this, you just need to point out the capacity of the node with this resource and start putting this resource in the request block. In terms of the request block, it will look like this. Apart from CPU and memory in the request, we can announce our own resources here. It's the disk I/O for read and write.
Соответственно, эти же ресурсы мы должны прописать.
The same resources should be written in the node, capacity node.
Ну, соответственно, получим работающий планировщик.
And we will get the working planner for the disk I/O. How do we set the capacity nodes? It's not that clear. So we established an additional capacity node or capacity for the disk input-output. Initially, this resource is created when a new node is established. When this information in the IOBA is perceived, it creates a new node in the waiting state. Then what does IOBA do when getting this resource? It gets the new waiting resource. We don't know the state of the node, so IOBA does a very horrible thing. It marks the node as the closed from planning. So it puts a taint there, which prohibits new pods to be planted on that node. We do that because we decided not to count the nodes where the disk I/O limits are not shown. We do not count it with this resource marked. So we exclude it from planning in order to avoid any basis running on it, databases running on it. Then we would like to get some characteristics of the nodes from the catalog. We try to characterize them. That's why ideally we would like to make sure that information from the nodes is written into a catalog. We'll have a limited set of config where we will be picking up all of the necessary characteristics just to make life easier for us. It's an ideal, perfect picture, and it does not happen like this all the time. So in the node catalog, sometimes there will be missing information about these nodes. In this case, we launch a special job which runs a benchmark of the node and measures the bandwidth and the maximum number of I/O per second that this node is capable to withstand. After these two stages, we get some of the two paths of capacity node for disk I/O. We get this capacity in our resource and we change its states to applying. So the status should be applied. After IOBA gets the applying state of the node based on the resources in the capacity, it fills out capacity node. So it shows nodes in the resource, and Kubernetes, this information about nodes is also stored in resources, just like pods, deployments, and similar ones. So IOBA with the Kubernetes API sets capacity of the node for the disk I/O. Then it includes the node into planning and it changes the state of the resource to applied. After IOBA points out this node with capacity information, then in the request block for containers, we show the new resources allocated for the disk input-output, and then we'll be able to work with the planner of Kubernetes, and the planner will take into account our new limitations as well. Here's the transformation of the custom resource. First of all, it's empty in the waiting state, and when everything is turning into applying state, and all of the capacity nodes are shown here, and it works great. We've taken a look at what we do with the limitations of disk I/O in Kubernetes. Kubernetes has interesting primitives for persistent data storage. They work quite well, and they're quite easy to use. The new Kubernetes have some limitations for disk I/O, but just initial limitations. It actually is suitable for using thousands of databases, which we showed in our example quite successfully. If you don't want to wait to the fully fledged input of the disk I/O, if you really want it, these functions are not that suitable to you, just like to us. You may do the same thing on your own, and it's okay. Thank you very much. I'm done. With the QR code, you can download the slides if you like, and if you have any questions, you can ask these questions right here. Contact me via my email or my Telegram messenger. Thank you. Thank you very much. Let's just vote for this report. You are evaluating this excellent presentation, so I'll start with questions that we have here. What if we create a new pod after we apply a limit? Interesting thing, we also thought about it. In IOBA, we added a new controller which follows the pod changes. The situation is dubious here. if we create IO limit, IOBA looks for pods that are related to this storage. If a new pod is created, IOBA looks for IO limits that are related to the same pods as the storage. So it creates a connection with the IO limit. Okay. What about the LVM pods moving from one physical node to another one? DRBD, CLVL, or SanDisks? It's not a very frequent operation. Basically, it's not a very frequent situation, but when the node just breaks down, if everything gets bad, we have backups and replications. We have a separate rescheduling operations. We have descheduler, which sees that we would like to remove the pod from the node, and it checks whether we can safely throw away this pod from the node based upon the replication data. So if everything works well, if it's not a master replica, we can simply throw it away, and through replication tools, we will get a new replication, and we also have backups as well, just in case. What if we move it from the BD to a new node? Will the data migrate, or the data will migrate on the old node? The scheduler allows to throw away some pods from the nodes. So we enhance the instance of the base from the node, and it checks whether this security is applicable here, and through replication tools, we do that. What are we going to do if we forecast IOBA with mistakes? Can you change the parameters on the go, on the fly? Yes, because it's one of the advantages that we get here. And the application is not standing still. So the application does not notice that, apart from the speed of read and write on the disk. Well, the guys developed that on their own, but without PID. But did you check actually the cab, which puts its marks in the containers? Yes, we checked that. I don't really remember why it was not suitable for us. I think with every resource it was more convenient to do with a custom resource. With a custom resource we can do it in a fully fledged way, so it updates in runtime. Probably there was a problem there. They were talking about making a neat container and other things, and some of the things were much more convenient, so they could exclude that PID stage. They did that. Can you apply this for long-haul NFS networking storage? Yes, basically you can do that. So there are some subtleties there. It would be best that the implementation of CSI for network storage would isolate these devices so that we can split the limits for different volumes. Basically, you can do that because the limits are put at the control group. So that's what is done on the side where the pods are launched. So it does not very much depend on the storage, but we did not try that. So we've run out of questions here. Maybe somebody would like to ask a question from the floor. I'm Evgeny. Thanks for your presentation. A question I have is as follows. You have planned your volume, you've scheduled your volume, you've measured its capacity, you applied this volume to the pod, and then you just manually changed that. What we're going to do about the planner, the scheduler? Seems like that I can bypass the planning mechanism by showing smaller limits initially, and then you change them to the top. And then I will be creating problems for everyone. So the guys who wrote the questions to you, saying that why we have to put it in mind, because if the pod is scheduled, it would not be
эти вот лимиты, и для того, чтобы
unmutable,
кто-то умный не пошел это и не
so
сделал,
that somebody would not do what I've described, and you can reschedule the pod, and it basically protects the system from such violations.
Один нюанс, что мы
So, just one subtlety, the custom resources are used for limits. So when pods are scheduled, only requests are considered, and the requests are described in the pod. If somebody decides to change requests, there will be a standard scheme. If somebody decides to change the request for CPU, it will be the same behavior. The custom resources are used for limits, and the limits are not taken here. They're not taken into account. Even a CPU in a pod will reach the limits to the top in terms of the scheduler. Nothing bad happens because the requests remain the same. Yes, it's right. It's correct.
на основании лимитов ставите,
But based on the limits,
планируете под. Вы
you're
запланировали под.
planning the pod. You're planning this pod.
На под.
Imagine that I have 10 IOPS per pod, and you apply this to volumes, and then somebody changes this manually. When they have access, they have a limit to this volume, it raises it to the top, and your limits to the custom resources are reached. So next time the odd goes to the node without the bandwidth, there will be no more bandwidth available and no more capacity. So this is how it works. So with pod we can do the same. If we reach the tops on the pod, it will start using the CPU power, and nothing limits it from that. But by requests, you can schedule quite a lot of pods there. The standard scheme does not protect from that. It's just a question to the users of Kubernetes so that they will be more adequate in planning. So, for example, they request 5 units from the CPU, and the limit is 8,000 units. It will not schedule, that's the point. If I reach the top with no capacity, the pod is not scheduled, but if I had installed less IOPS requests, it would be scheduled, and then I go to custom resource, tune it to the top, and in C groups, the number of IOPS will change per container, and I will consume more resources than it's pointed. That's what I'm talking about. As far as the data non-consistency, that's another thing. We are not showing the limits in the pod. We have the same point of truth. It's called custom resource, because for our own types of the resources, the disk I/O, for instance, we cannot set the limits that are different from requests. There is a difference. For CPU memory, we can do that, but for custom resources, we can't. We can't separate them. So we decided to do the separate resources for that type of thing. So the only single point of truth is a standalone resource. That's where we store it.